Okay, we've got a really painful lecture to do today. It looks as though some of the class anticipated that. But we have the algebra of the Lagrangian treatment of this ghastly war machine here. And I want to talk about one more kind of equation that is the last on the list on the wall over there, and that is the one that involves the Riemann equation. And we'll get that in a very pedestrian way today, but I want to point out, for those of you that may be headed to the field of general relativity, which is part of our department, certainly, the equation that I'm talking about, if I can get this guy here to show up over there. There we go. The equation I'm talking about is right here. And the second Riemann equation is some kind of contravariant force, it's called the contravariant equation, equal to the contravariant coordinate double derivative in time. And then these things called Christoffel symbols, which we're going to talk about in a couple of lectures from now, give the curvatures effects of whatever coordinate system you're working with. So this is a very GCC coordinate system. It's also the one that works for relativity. And what comes out of this one is that we end up setting the force often to 0 and make one of the coordinates time. And that's the thing, at some point classical mechanics has to get with modern physics. And getting with modern physics is taking full account of wave mechanics and relativity. And those two we're going to talk about at the very last lectures of this class. So I want us to get started on this formalism that goes with that, and it works for any of the classical mechanics, whether you're using Lagrange or Hamiltonian methods. We'll talk about that in the next lecture. But today I really want to concentrate on just the algebra and the geometry associated with this. We mentioned a little bit of it already, but I want to go through it again, and I've given you a couple of problems that involve understanding the measurements of distances and areas and volumes using these curvilinear coordinate systems. So that's what most of today's lecture will be. At the end, when we get the Riemann form for the equations of this device, I want to try to second guess this. Now this is something that's in the textbook, and it's probably better for you to read it, but we'll try to make it to that point. Okay, let's remember what it is that we're talking about here. As I said, the basic idea of this is sort of making this into a physics fairy tale is, could Galileo have come and told the war makers or whoever they were that had the trebuchet how to make a better one? And no chance of that. A tremendous amount of mathematics had to happen before Galileo's discoveries led to Newtonian and finally to what we do in modern mechanics. And then also, with a trebuchet, there's no analytic solution for the trebuchet driven by gravity. Now what we will do today is stop in the middle of it and talk about the Chinese trebuchet, which is the one which about 100 warriors gives a pull to the lever and gives it angular momentum, and then it opens up and throws something. So that part of this lecture will be coming up in the middle. But what I would like to get to really quickly here, just to go over it one more time, is the idea of having two sheets. That is, having a torus as the, shall we say, playground for the two variables, theta and phi, of the trebuchet. Remember, the phi is the variable of the throwing arm, and theta is the variable associated with the driving arm. And if there was no gravity, or if there was a very light gravity, we could have a trebuchet on the moon or some asteroid, it would make sense to have it run by just giving it a force like the Chinese did 3,000 years ago. And it would then proceed to take that momentum and somehow get the kinetic energy into the object that is to be thrown. And that's something else we'll talk about later, is that if you do the analysis that we're going to do today and then use the Hamiltonian instead of the Lagrangian, you discover that it has the same numbers for a particular, well, the most common trebuchet, the one that's in the NOVA presentation. It has the same numbers as the superballs that we started this whole class with. And I still haven't figured out why that is. I mean, why the simple superball thing is hidden in the mechanics of this. So you want to get a few extra points, you figure out what's going on there. In any case, the idea of having covariant variables, I want to make sure that we go over again what it is about the covariant vectors in this case, as well as the contravariant ones. And the contravariant ones are the ones that work best for Hamiltonians and Riemann equations. The covariant ones make a lot more sense with regard to a Lagrangian problem. But having these two, and let's put it on this screen right here, having these two surfaces, that is, a surface here that looks three-dimensional, it is not three-dimensional, it's just two-dimensional. That's also true of the ones that I've given you in the homework today. There's one there that looks very two-dimensional and flat. There's another one that's similar in its geometry. It looks three-dimensional, but it isn't. This one isn't either, but if you want to put it on a torus, you can. And that makes sense to do in this case. So I wanted to show very clearly how those coordinates work. And it happens I have to go to the old program that we first wrote for the trebuchet to show you this. And you can see here, for example, that if I put this thing right on an intersection right there, and then it will do what's pretty obvious. That is, it will follow that circle right there of the top. Now this particular trebuchet is in a left-handed position, okay, folding this way. As I follow this over the place where the Jacobian goes singular and keep going, there's nothing there for it. Now I'm on the other sheet, you see. So that in that sense, this thing is kind of three-dimensional. Same thing when I come in the bottom here, you see it's not touching anything over there. It's the bottom sheet that has something that it's following. Okay. Now the one that's more weird, if I go from this point and use the beam, you see what the beam does when I go around. The same thing, except remember, these are lab-fixed angles. These angles are measured relative to the x and y coordinates that you see on this thing there. Same thing happens as this thing goes from left-handed to right-handed. There's nothing for it to follow down here. It's in the middle of nowhere down here. It's on the other sheet. It's now a right-handed trebuchet. Okay, so I wanted you to make sure you see that. And then when I give some problems later on that have to do with this geometry, you won't be as puzzled. Okay, now let's get busy, I guess, with reviewing the covariant, contravariant stuff that we first introduced with respect to polar coordinates in lecture 9. I want to make sure that that's all coming. As far as the OCC coordinates, most of you did that perfectly. You'll now have a chance to try it out on these crazy unprofessional parabolic coordinates, two of which I've given you as homework. In any case, the important part of this has to do with the fact that the first differential of the position vector R, first differential has a partial derivative describing the covariant vector 1 and 2 to go with the differential Q1 and Q2, and that's probably shown better. And let's get rid of this old program here and get back to this one, which is coming up shortly here, I hope. So it'll take some little time to get all these things coordinated here. The basic idea of these covariant coordinates involves realizing that they have to do with derivatives. So I want to make that point, that this thing right here, this E1 or E2, follows the tangent. It points in the direction of the tangent at the point in that curvilinear coordinate system where it's based. So it is tangent to the thing at this particular point. Now you go and look at this coordinate system with a microscope. It will look more like the sketches that I was giving you and will be giving you here. But again, I'm trying to picture here a curvilinear coordinate system that's just two-dimensional. It kind of looks, your eye trying to see the sheet rising up out of the screen, not what I want you to see again. So at this particular point, we're talking about the tangent. Well, that's exactly what you're getting when you take the derivative. Okay, since only Q1 varies. When you take a partial derivative of the position vector with respect to Q1, that means Q2, the other independent variables of more dimensions, they will all be constant. So only Q1 varies, the others remain constant. That's being a tangent. That's what you're doing there is just following the line. Now, that's fine. This is the blue, what we may call the democratic way to go to things. This is the Republican. This is the rebelling. Okay, because what we're talking about here for E super 1 as opposed to E sub 1 is the partial derivative of Q1 with respect to the vector R, which is a gradient of that coordinate Q1. And you have already probably learned that the gradient is always perpendicular, you see, to the Q2, in this case, surface is E super 2. E1 here is perpendicular to the Q1 equal that particular constant. So E1 normal to Q1 equal constant. E sub 1 follows the tangent. So that, I think, is important. Now you see this is the Q2 equal being a constant. It's only Q1 that's varying here. Here it's a very different situation. The normal coordinates are quite good. So, okay, is this something that makes sense? I want to make sure that that's understood. This little geometry that happens with covariance and contravariance. Because we want to make use of the fact that these guys are making Cartesian product. That is, this is 0 unless m is equal to n. And in that case, it's equal to 1. So you get yourself to have orthonormality by using these two in concert. And we can talk later about how these go with extensive quantities, these intensity. That's something else that is a little iffy, but it's important. Okay, now when it comes to doing this particular problem, where we already have some relations involving Cartesian versus the, in this case, GCC, theta and phi, and it really is GCC, it's the torus, two sides of a torus, so to speak, that make up this. And this is again stuff that was in our the last lecture, 14. You can go back and look at that, and this is a picture of it. Here's those tangent covariants lining up with their respective coordinate curves that I was showing you just a few minutes ago. So, having taken the derivatives properly, and I'm doing them with respect to Q1 and 2, in this case theta and phi, I come up with those two vectors, and there they are. And of course this can be scaled any way you want. The derivatives in a geometrical thing can be this big, or they could be microscopic like that. Here I'm writing them at sort of a 1% scale. But anyway, this is what I want you to get familiar with, is how to read, how to think about first the covariance, first the tangent space, but we'll do the contravariance as well at the same time. Okay, so I'm getting ready over here to put the Contras up, but there's what we just talked about on the codes. Here come the Contras. I put the codes in there just for the sake of it, and they're, as they say, the ones that enclose the actual coordinate grid that goes with the problem. Makes a lot of sense, and this is why they're good for Lagrangian mechanics. And right here, I'm showing where they live, but this one has got E super phi here, and it's constant. It's a gradient of phi equal a constant. Phi equal minus 0.1. That's this line right here, and it's just a straight line because I'm looking microscopically at this. We're talking about infinitesimal limit. And then the other one, the E theta here, points perpendicular to phi equal a constant. And everywhere on here, this would be a similar deployment of the contravariance and the covariance everywhere on that surface. So once again, theta dot super theta dot sub phi is 0, but the product of them with each other, theta down, theta up, that comes to 1. So that I want to make sure. Now this is back to lecture 9 again, just to point out that there's 3 different ways to look at geometry. There's what we call the Estrangian approach, which really this is, when we make use of the dual space, that we get that kind of in passing. But then these are the guys that are going to go with Hamiltonian. These are the guys that go with Lagrangian, more or less. And we're back to polar coordinates, just ordinary polar coordinates, as opposed to our Lagrangian that goes with the trebuchet. So let's go ahead with a trebuchet a little bit here. There are a couple of things I wanted to show. And that is, after you have calculated the Jacobian and gotten out of the columns or the rows the covariance, in this case, we're talking about, there's a covariant out of the first column, there's a second one for phi out of the second column, and here we're pulling them out of the rows. Okay, the E super theta and E super phi is coming out of there, but this Jacobian is the inverse of this one. So that's the price you pay for Hamiltonian. Hamiltonian, you'll be working with the inverse of the Jacobian, and if things are the way they usually are, you're given functions of x, given x, y, and z as functions of the queer coordinates, you're going to be ending up with something a little more complicated because it has a factor that's a function of the variables, the denominator. And this is a factor that blows up when the trebuchet arm and beam are on top of each other or opposite each other. This thing blows up, you see. Got a zero in the denominator when theta and phi are equal. So that's an important difference that the contravariants are going to give you. But as you put together the scalar products of, say, the contravariants or the covariants, put them together, this one produces what's the most common thing that's used for metric in relativity, the covariant metric tensor here. Now we haven't stuck the mass anywhere in these drawings here. There are two masses that need to be stuck in there, and we did that already, and I've just taken it out so we can see the geometry of just the torus without worrying about that. But when we do that, and we'll do that shortly, I don't use the letter G, which is the common letter for writing the metric tensor. G mu nu, okay, it's a thing that Feynman used to joke about. He said that he was stuck going to a conference on general relativity, and he got on a taxi and got lost, and he went to the wrong hotel and there wasn't anything going on there, and so he asked the taxi, where is the conference on general relativity? And the taxi driver, what? And he said, where's the conference where people are going, G mu nu, G mu nu? He said, oh, that's down the street, and took him right to it. So it helps to have G mu nu in your lexicography for going to these things, and at least it did for Feynman. Anyway, this is the covariant, and this is the contravariant one over here. Again, more complicated, just as this is more complicated. This is squared more complicated for the contravariants, the Hamiltonian. So stuff we'll use in the Hamiltonian. We'll be sticking mostly with this for the Lagrangian. Okay, now let's see if there's anything I can say that's more than this. Go ahead and get this up to speed here. The full geometry that we're about to do is going to be making use of this. This, of course, is the good old polar coordinate system, but here's where we are right now with respect to the double polar, or whatever you want to call a trebuchet. And we do have one more, or a couple more things here to mention, and that is that the product that gives G mu nu, GMN, in our non-Latin approach here, is a Jacobian transposed with a Jacobian. So you look at the transpose of this covariant Jacobian with the non-transposed G mu nu, put those two together to make the metric. So that you know, if you're going to program this stuff, little points like that are worth keeping in mind. And that's, of course, since general relativity is notoriously difficult to solve for heavy problems, almost everything there is done on a computer from the very beginning. So, oh, and here's the contravariant ones, I guess, go in here. The K transpose product is just sort of the flip of this one, would give you G super mu nu. Okay, so tangent space, normal space. Here's where we get into the idea of, well, transforming from one to the other. That's pretty easy to do with the G mu nus. But also transforming a particular curvilinear coordinate system to another one. We've already transformed from a Cartesian coordinate system just to make these diagrams, but very often you need to go from one curved coordinate system to another to match boundary conditions or something like that. This is all stuff that relativist guys have to do. Now, that's why I'm saying here that there are lots of ways to express, in this case, a vector, but later tensors, in terms of the unitary vectors. They're called unitary vectors in almost all of the math, but has nothing to do with the word unitary that quantum mechanics uses. But there is a connection in the sense that I've already mentioned, I think, that the covariants are kind of like the kets in quantum mechanics, and the contravariants are kind of like the bras. I'll make that point a little bit later here again. But that's the beautiful, the beauty of mathematics, and using it properly, using it carefully to take advantage of the dual space, which is something that hides in some mathematics books, barely mentioned in, well, mechanics books, practically not at all. So anyway, always you have a vector written with bold face as something that has to do with a physical something or other. In this case, let's suppose it was a velocity vector, okay? And the idea is that that velocity vector can be looked at either using the covariance or the contravariance. That I've already made the point. But it can be looked at using other curvilinear coordinate systems. I'll call them the barred system. No reference to the Attorney General that we're having so much trouble with. But the bar system, okay, here is just a completely different set of coordinates that will have components that are also indicated by putting little bars over at least the indices, but sometimes the actual v variable components of the vector. Same thing over here using the contrast. So you see, any vector you have, wherever it is, can be written 4 different ways. First using the bars, and then using the unbars. Here using contravariant components with covariant vector, or covariant components with contravariant vectors. And the idea is that the co and the contra cancel each other to get something that's invariant. Invariant to all of the choices of ways of looking at the thing. Okay? Change of basis is what you call it in quantum mechanics. Here we have lots of ways to change the basis. You hardly ever use bras for an actual representation of something. But when we start playing with antimatter, you're going to have to, if there's as much antimatter as matter, you've got to work with both of them. That's really what this is getting at. That's physically what's behind the mathematics of this many ways of describing things. In any case, as you can see here, the way you figure out what that component is, for your, if you know what your vector is in some other way of writing it, say the original x, y, and z Cartesian thing, you simply dot it with the vector, either contravariant here if you want the u contravariant component, or over here if you want the covariant component, you do a dot with the covariant vector. Okay, so that's the definition that works very well, and that's because of the fact that these things, covariant and contravariant, are orthogonal to each other. The gradient is always perpendicular to the tangent. It's really what's behind all of this stuff. Okay, so then it comes the question of how long is a vector. And there's lots of different ways to make the vector. The first and most obvious way to make this vector is if you're going to use contravariant unitary vectors. If you're going to do that, well, that just means that you've got this much. That's the v phi here, okay? But right here is v phi, here is v theta, down here, okay? But when you write the vector, you don't worry about the metric tensor at all until you actually want to know where that vector would be on this graph. How long would this graph be, you see? Okay, well, there would be v phi long, but you've got to use the right metric. Now the metric comes and tells you what's the scale factor that you need to attach to that v phi that you've written here to actually get the length of the vector in this contravariant description here using this contravariant E phi. Okay, and the length of this thing is the square root of E phi dot E phi. That's the square root of G super phi phi. Over here, okay, if you're talking about phi, but now doing the covariant, if you're writing your vector like this, okay, like this, exactly like that, okay, you've got the covariant guys right here, going with contravariant components, okay? So I use this particular component times this guy, but this guy isn't a unit vector, he's a unitary vector. The vector, the actual vector that you're looking at, the length of it is going to be this quantity times the length of this. And the length of that is E sub phi dot E sub phi. That's defined as the metric coefficient G phi phi. But of course, you got to take the square root of it to get the actual length. Okay, well, if that's all you ever did, that would be the end of the thing. But we are used to taking vectors and projecting them perpendicular to the axis as well, right? Okay, I'm going to let you figure that one out. Turns out it's this inverse, and that's what that homework problem is to fill in all the blanks for a diagram like this. Okay? So I'll let you take this puzzling, being aware of that relationship of the metric coefficient. Okay? And we've only done a little bit here. That's what I call the covariant projection. There's nice names for it. Okay, let's see if there's anything else. Yeah. Oh, yeah. Go ahead.
Yeah. This product, whether it is contravariant, covariant, or vice versa, looks like we would left with just some number instead of vector.
Well, the numbers that would be part of your physics would be these guys.
Right.
And for this coordinate system, now a completely different coordinate system not drawn here, okay, would be this one, you see. And it might be that this one has really good at solving the problem, whereas this one is a good one to write the problem down to start. I mean, that's what it really boils down to. In quantum mechanics, there will be certain kets or bras, but you work with kets mostly, so you're working covariant, and it will be that there's some obvious ways to set the problem up using a certain set of vectors. And then it turns out that there's some transformation you could find, maybe using group theory, that's my favorite way of doing it, but whatever, where you have a set of completely different vectors that solve the problem. Say you want just to get the eigensolutions. Find those very special vectors in this gigantic space where the Hamiltonian hits them and just gives a number. They're eigenvectors. Okay? I don't know if that answers your question, but that's why we're doing this. You set the problem up in one set of coordinates and then you solve it in another one. And then the trick is figuring out how you get to that other one.
What I'm asking is that, for example, over there, on the right side, we have some, just the right side of the equation.
Oh, this side.
Right. We just have the sum of two brackets, which is a number, and on the left side, we have a vector.
Yes, which is written with no indices at all. You see, the idea is that this is some, say, an electric field in at a certain point in space. Okay, or a vector potential. It could be A. All right, whatever. Let's take electric field because you kind of can feel one. You can visualize, and you stick your finger in and you go zzz. All right, so there's this physical thing there, this V, okay, and what you want to do is express it some way using the E's or the E bars or the E supers, whatever, okay, whatever happens to work. There's a lot of variety a choice here. But once you've done, those are the numbers. They may even be complex. In quantum mechanics, they're almost always complex. Here, totally real. Okay, so they have two numbers here that really mean something. And if I decide I want to use these guys, this doesn't change. It's just you change it, look at it from a different coordinate system. Okay, so that's the game we're playing. These things in fat letters in later tensors, the same thing. When I have a second rank tensor there, okay, that represents some object in the laboratory. So it could be a measuring device. And it doesn't give a darn how you look at it, but when you write it down, you have to decide what a frame you're going to look at it in, and you'll get a certain set of numbers that are the components that we're writing here, covariant or contravariant. But it's, the idea is that looking at it doesn't make any difference. You pick a different way to look at it. Oh, okay, I can go do something with that. But I could get started using this set of vectors over here.
So for the starting point would be just use Cartesian.
Well, that's true. That's
So
true.
those
And that's
little
what we
b's
do.
will be 1,
Yeah, in
0, and 0, 1 for the
Right.
2D. So you really are, you're showing how many of those basic vectors you need to add
Yeah.
together to get the whole.
Yeah.
And your starting point right here is to use some covariant vectors that are expressed in terms of x, y, and z in the upper frame. That's what we call the Jacobian, right? Then the Cajobian is the flip of that. Right. Now your coordinates are upstairs instead of downstairs. So there is a curve GCC vector coming from Cartesian coordinates in this case.
It's
But
all there, but you're,
Cartesian coordinates are terrible for doing spherical things, right? If you've got a hyperbolic quadrupole field or something like that, Cartesian, well, you want to get out of them as fast as you can, get into the hyperbolas, right, that actually describe physical fields. Does that help at all? Is it, sort of an analog? And there you're just using OCC, but what if you're talking about some crazy field that's due to a wave that's gone through a lot of changes, so it's all over the place? Use that as your coordinate system. And it's GCC for sure. So that's why I'm selling you this particular mathematics to do that job. Thank you for the question, but that's, this is philosophy of the mathematics.
it's like
as
we're
it applies to
overwhelmed
physics.
with twice of what we really need to work with, but we're covering both right and left-handed at the same time, so that they work in phase.
Yeah, there's a little bit more I want to talk about this, but basically the dot product is all you have to do to solve that little problem I gave of identifying these things. So the other thing that you may have to do, and this is go from Lagrangian stuff to Hamiltonian stuff, okay, if you want to write a contravariant vector in terms of the covariant vectors for the same coordinate system, okay, this is not a transformation from these guys to these guys. We'll talk about that later, but in just a bit here, I hope. But here's the basic idea: is that this contravariant vector could be written as some sort of contravariant thing, okay, that is an n component times the covariant unitary vector. So I'm trying to express this thing there. Well, how do I do that? I have to use a scalar product associated with that m and n. And that is nothing but the contravariant metric. So this is why the contravariant metric turns a covariant vector into a contravariant one. So that's a transformation that you should not forget. If you have to go between the blues and, well, here now they're colored green. I did the blues and the red over here, but we're being nicer colors, but they're different colors. So I do need that matrix. And the way to think about the thing is, this is a contravariant metric with a metric upside. You have to sum over the n here. It's repeated on the same side of the equation. That's why we don't have any sigma signs cluttering up the mathematics here. But the idea is that this matrix, multiplying by this these vectors, summing over these vectors, gives me a contravariant. So I express one of these vectors right here, the contravariant, in terms of these two. So I can actually express something that's in what we call the normal space in terms of things that are in the tangent space. So that's one more trick that sometimes becomes useful. Okay? Same for covariant of vectors. I can take a contravariant to a covariant just by using the lowering matrix. It takes the... Now this is something you don't do in quantum mechanics. You don't turn bras into kits. Here you do play that game quite often. Okay, let's see if there's... Better bring some of these boards up to speed here, just to have things to look at that make sense. Here's where you go between some curvilinear coordinate system. You come from Cartesian now, but you need to go further. You need to go to the barred system. Okay, how do you do that? And that is something that's really quite beautiful. I call it the chainsaw sum rule, but it doesn't have anything to do with the horror movies that involve chainsaws. It's basically what you do is you say, I want to turn my contravariant vector here, m, into a combination of contravariant vectors involving E bar, M bar. Okay, in other words, a whole set of things that have bars on them, whereas I didn't have that here. So what you do is you take your chainsaw out and you chop the partial derivative in half, bring the r on to the side, either this side or that side, and then you put in a whatever you want to go to. In this case, you want to go to q bar, so you sum over m bar. So you get, in this case, two terms, one bar here, and then another one with 2 bar, okay? And the Jacobian now, between those two unbarred and bar coordinate systems, is giving you a transformation. It'll do it. The same thing works for the components as well as the vectors themselves. Well, I'm just showing it for the vectors themselves right here. So that is something that's really cool. So if you want to do it with contravariants, go for it. You use the Jacobian that looks like that. You want to do it with the covariants, that's what's over there. You might as well put it over here as well. Okay. I do the chainsaw, I saw them in half here, and I put whatever it is I want to go to in the blanks. And I want to go to barred things, so I stick them in there. Bingo. You've got a transformation, because there's the m and there's the Jacobian that goes between bars and unbars. It's the inverse of this Jacobian right here. It takes you the other way. And that's all there is to all of those fancy transformations you have to do if you're doing relativity. Okay, and I'm selling relativity rather highly here. But if you want to do optics, quantum optics, you'll be just stuff like this. And boy, you need quantum optics if you're going to do any sort of solid state physics these days. Okay, so I just make points about this business here. And here's the other thing. If I want the components with the contravariant indices, I do the same thing. That I use the same transformation for this. It's really quite cool. And as I say, these have quantum equivalence. And of course, in quantum mechanics, they're all complex variables involved, but they're still numbers. So you have the same sort of thing. Basically, what I'm saying here is you want to convert this particular kit right here to a combination of barred kits, well, you simply have to put in what's called a completeness relation, a sum over kit bars. And you have to arrange it in such a way that it makes sense, but basically what happens here is this little kit here comes through, makes a scalar product. It's just like the scalar products that we're talking about here. In this case, it would be an E contra M with an E co M bar. Okay, a dot product of those two unitary vectors is what's going on in all of this mathematics. Here's what you do in quantum mechanics. You've seen this, right? In your quantum class? Okay, the completeness relation, we always stick a sum over those things. That's equal to 1, right? In quantum mechanics. That's your unit operator right there. When you do this, that's your unit operator. It's pointing to that thing, which is definitely not an operator. That's the result. But here's the thing that you use, a ket bra. Okay? And then you make a bracket that goes there. So basically what you're doing is you're saying, I have a vector m. I want to change it, so I'm going to multiply it by 1. But 1 is equal to any sum like that. Bingo. You've got a transformation in ket bra language. Is that's stuff you've done, right? Yeah. This is just the other side of the world in mathematics that goes with classical stuff. So these metric relations are really important. Now, this kind of transformation, it'll be a new kind of quantum mechanics, and someday we'll do that, but we're not doing it now. We don't have that option in any of the stuff that I've seen in literature so far. Okay, now I'm going to go through this fairly quickly because it's stuff that you should probably just go and read in either the text or go through the lecture notes on your own. When it comes to doing area, okay, if I have the area associated with this vector, which is the E1, here's our E1 would be the theta, I guess, and then E2 would be that. You don't vectors like that. If I have those two vectors going here, there's one, there's the other, number 1 and 2, and the area that is enclosed in two vectors, simple vector geometry. I think we have already talked about this a little bit when we talked about angular momentum having an area associated with, is conserved in isotropic orbits. You remember that stuff? Well, here I'm using that cross product, okay? And so I need the length of that cross product, which is this. Well, that reduces to this. This is a simple identity, and you should use complex numbers if you really want to prove this. But this is the E11, E22 minus the dot product of E1 and E2. And of course that's symmetry. And so when you say that that's the area that's enclosed, say the area of one of the cells here, this guy right here, that's what we're after. And you have to then realize that the components that we're using are bogus components. They're multiplied by scale factors. This is where you need to know what the scale factors that the metric are giving you at every point. But the metric is sitting right there. So the answer is the product of the components and this determinant. Okay, this is the determinant of the 2 by 2 metric matrix there. That's the way you would normally write it. Okay. Well, this generalizes to other things. Obviously, the same thing works with the Contras. If you're finding areas in the tangent space, suppose a normal space, that's the tangent space over there. This is the normal space. Okay. So area and volume, and once again, these guys are got to be inverse of each other, so you can get one from the other very quickly. 3, oh, that looks like it's going to be a hard problem. Well, it isn't. Finally, you're going to do the theory of determinants. But every time you look at a volume, and you know from your vector analysis that x cross y dot z unit vectors, okay, or not unit vectors, that would have components, whatever they are, would make the product of those, and then this thing boils down to a determinant, okay, a determinant of the Jacobian. Okay. Now, the metric tensor is the product of the Jacobian, the J transpose dot J, or the flip of that if you're talking about contravariant things. But that is that's a quick course in the geometry that's associated with this crazy system of covariant, contravariant vectors. Okay, if there's anything else here that I need to say, I think that is, here's the contravariant Jacobian. Now it's K dot K transpose as opposed to J transpose dot J. So these little nasty little differences will make a big difference when you actually go to use this stuff. Okay, let's use it now, but it won't be G mu nu, it'll be gamma mu nu. Just coming back again to the stuff that we did in the last lecture, it's about page 80 or so, we write all this out finally. There's a matrix proof to this on page 80, but if you just use the normal way of writing tensors, this is an expression here giving the kinetic energy 1/2 some kind of thing that has masses and geometry all mixed up, but it's basically a metric coefficient that's had an m multiplied and then another one for any other coordinate. It has a big M in this case for the trebuchet. That's a really compact way to write this thing. That's the matrix way to write our particular example here. And we already have these coefficients, or have made these coefficients. This is the covariant metric with the masses. You can see it's mostly little m. This one's going to be thrown. There's the driver right there. That's the only thing that it contributes to this. So we've done this now, and this is an expression of the covariant momentum, Lagrange's definition. Here just involves the kinetic energy. The potential energy is not allowed to have velocity dependence. If it does, it's a whole different thing. We'll talk about that when we do electromagnetism. But here we don't have that. So this would be the same as the derivative of the Lagrangian. The V is going to have no contribution from a velocity derivative. So this is the way of writing the momentum in terms of velocity. We've made this point already, but it doesn't hurt to do it again. So this idea of momentum tensor, there's the algebraic proof of it. That's what we're using here. So here are p theta written out, p phi written out in all gory detail. There's just the actual algebraic expression. So we're doing a lot of fancy stuff with these metrics and everything. If you don't want to do that, it's what most textbooks do. Just go directly, in this case of this problem, directly to this by taking that partial derivative. You're done. But you see, this is arming you with something where you can visualize what's happening when this mechanics gets going. It starts doing things. So I'll go ahead now, and here's where we have to do the algebra in quite some detail to figure out how the trebuchet is going to be run. Well, what we're figuring out really is equations to put on a computer. So all the simulations that I've been showing you are based first on an old-fashioned computer that I had the little Mac fire plug, I think was when I first did this stuff. But now, as thanks to TC's HTML5 word, everything here is just a rendition of this in HTML5. And we'll talk more about that later. In any case, we've got two jobs here. The definition of momentum is a partial derivative of kinetic energy with respect to the velocities. So that's part of our story. But we also want, and you see this guy right here, or this guy, they each are equal to some change in momentum, but in particular they're equal to some, shall we say, generalized force. But by that I mean torque. There are two torque equations sitting there that are going to be time dependent. And now you've got a lot of algebra to do. Everything that can change here, everything that can change in this expression from here to here has got to be accounted for when you're taking a total time derivative, and that's what we're doing here. Okay. So fortunately, as I say, m dot is 0. The mass is not going to change. Suppose it was, and it's a water that's falling out as it moved. R dot is not going to change. Let's suppose big R was a spring. Then it would change. We'd need to be taking a derivative, adding that to the equation here. You see. Again, if the little mass, the actual projectile, for some reason is changing, okay, as this thing evolves, okay, and the little r distance to that, L, the actual lever that throws it, it might be a spring as well and get longer, so you have to take its time derivative. So you see, this could be a lot worse. This is a very special, ideal trebuchet that doesn't bend or stretch. Okay, and its constraints are all ignorable. So we get four terms here involving sines and cosines from that. Okay. Now this is just a review of what it was. We have kind of already opened the door for this by writing Lagrange's equations, the first equations and the second equation, and finally writing the force equation right here, and then we even went to the point of making it a potential equation, which is the Lagrange equations that we know and love. So this is all stuff that's coming, and what we have to do is figure out, this is a torque here. I'm indicating that it's going to be a left-handed torque. It's got a minus sign on it. This is positive torque. Here I've got both, okay. The beam part, this guy, okay, is going like this because of a negative angle, but really that's what the algebra is saying, but you can sort of see that that makes sense. And then this guy is countering that, so these are fighting each other there. We're going to try to talk about all of that mechanics here, but we've got algebra to do at this point. So coming back to, this is really Lagrange's second equations. If we had a potential, we will, fairly shortly here. This, see if I've got anything that needs to be said at this point. Yes, this is basically the total force expressed by that, and we're busy writing pieces of that. First the P dot here, and let's take a look and see if there's anything else here I need to say that. Yeah, to finish this, I need the real gravity forces here. If we're going to play the trebuchet 12 in the medieval battles, we need, everything's going to be driven by just plain gravity, not 1,000 soldiers in the 3,000-year-old trebuchet, but actual big hunk of, a big crate of rocks are driving this thing. And so we need to put the values from this. Uh, you can click on this thing when you're studying this and go back, and there's things to click yourself back to this point or nearby it. So here are the things that actually go and do the driving for this. And that is a very important part of this. The change in momentum of the throwing arm, that's our output. This is the driver right here, and it's being driven by that guy, which has got the big mass in it right there. But it's also got this thing attached to it with the same trigonometric function to give this particular term there. Okay, so we go ahead here and get this thing to catch up with that. Here we're really putting the gravity forces in and collecting some terms that and one of the things that you'll notice whenever you do a lot of these mechanics things, if you write it out in a nice orderly fashion, you'll notice very often you have things that cancel. See this guy right here? Okay. And I've got the same thing, same minus term over here. And then this guy, he's the same as that, okay? So they're out of there. This thing at least simplifies to that point. But there isn't much else you could say for the algebra of this that is cool. I still don't understand why those, where those terms, why those that happen to go, but this is what we end up with here. This is the Lagrange force equations with those particular guys, and those are the guys that have the big masses, the driving mass, and then the projectile is there and there. Okay, notice they're minus each other, but not quite. This one has got the lever arm. This one's got the throwing arm, the long throwing arm as a lesser. So these are the things that we're actually using with. Now, the question that comes up is, and if you have a particular kind of a computer program that can work with a second derivative, it would be nice to have that thing exposed. And Runge-Kutta, there are Runge-Kutta routines that do that. They play off of the highest derivative, and in this case, second. And so, what you would like to be able to do, and this is the way the equation looks, these two equations look in a matrix. Okay, so here we've got the double derivative sitting off here on the right-hand side of the equation, and this combination has to be equal to these guys respectively. All right, so something has to be done to take that, make it work. Okay, and you see immediately, and this is something that pretty easy to see that this was coming. Just go back, but this is our metric, our gamma mu nu, sitting right there. Okay, so if I want to get this equation on the left-hand side, I got to go through and multiply by the inverse of this. That means I've got to take the inverse of this and multiply that together. That is multiplied by the forces, the two forces driving and driven, and get a Riemann-like equation, that has the double derivatives exposed, so to speak. So here's what it looks like before we do that. Okay, it's got P dot, and we could just stop right there and just use P dot and figure out what everything else is by making that a derivative of the velocity, angular velocity, which it is, it's an acceleration, so it's two derivatives. But it is often better to get that highest derivative exposed on the right-hand side. And that's why the Riemann equation is a winner for a lot of computer applications. So we've got to invert that sucker. But there's a cost to that. A denominator that's complicated. Okay? So, and this is kind of a super, I call it a super inertia. Okay? There's an mr squared right there. There's an mr squared that's involved in trigonometric function. The difference is as this thing flexes. And there it sits, and we have to make use of that. So I've got to go through, multiply that guy, the inverse of this guy, there. I have to then end up with the inverse of the force relations that we already had. That's this, you might call it the inhomogeneous term of this differential equation. Okay, we're going to turn it into just a single thing. That is, it'll be this guy right here is exposed. That's a Riemann equation right there, form-wise. Okay, this is speaking roughly. Okay, and then this inverse metric, this crazy thing right here with its super inertia in the denominator. There you go. That's where you would be able to get this thing on a computer. Now, what we're going to do with this today is see if there's anything else I need to say here about it. I think we have everything we need. Okay, there's that funny inertia, super inertia in the denominator. And what we'd like to do is, if you were really smart, and I am not, but if I was really smart, and maybe some of you are, I could just go and write this equation down. I call that second guessing here. We're going to second guess Riemann equation. Okay? Now I'm going to go through this really quickly because, well, we're running out of time. But what I want to do is see if I can figure out what are the forces involved here. For example, there is a centrifugal force associated with this particular moment of this trebuchet. I imagine actually a combination of forces, but let's say that's what it is. And I'm calling it a particular state of motion. I've got those variables at this instant, and I want to figure out how much is this pulling on the big beam, or reverse, how much is the beam causing that thing to fly outward. And that's basically what the trebuchet is doing, and that's basically what all of the sports that have to swing a lever are doing. And the idea is to get that end going fast, and a part of that is centrifugal force. Centrifugal force actually making that thing go fast. Okay, so that's what we'll be selling you as a way to second guess all of this algebra that we've got to this point. That's going to go on the computer, and you could just forget about the whole thing. But it's kind of a hobby of mine to see if I can second guess some real complicated thing like this. See if I can pull this off. You see. So really, what we're asking about is rate of change of the phi angular momentum around this pivot. If we could write that down, that would be nice. I mean, basically, I've got acceleration of phi, and I've got the acceleration of theta equal to that. That's the equation of motion for this thing right here. Now, I guess I have forgotten to mention that I'm switching to the Chinese trebuchet. I'm switching to the one that gives the thing some angular momentum, gives me some initial values to those. Okay, so I've got 1,000 soldiers that go like that with trebuchet. And supposedly the force that they're doing, just like our Super Bowl experiment, is negligible. I mean, is huge compared to the gravity. So the gravity that's being exerted on that. So you can either call this the Chinese trebuchet, or you can call it the trebuchet on an asteroid or a moon where the gravity is negligible. That's the problem we're doing. Okay, there'd be a lot more terms in this if I don't do the simplification, okay, idealization of the whole thing. Okay, so here's kind of where we stand with respect to the phi variable, which is the one we're interested in. We're interested in getting that thing to a high value, get that phi angle really going. So when we let this thing go, it has a lot of velocity. You know, this is a, and the trebuchet, this thing is really long. It's so long when you tuck it in. It's just close to the pivot. That's the Kenilworth trebuchet that beat up a poor old historical castle. So I'm going to move all this stuff to the top of the screen here. Boom. Start over again a little bit and talk about how we think about the forces, in particular that one centrifugal force right there. Can you say something about that that makes sense and finally gives you this result instead of having to, well, if you, as I say, if you were really smart, your competitor would be sitting there doing the algebra, still doing the algebra, and you would just come up with the answer. Is that possible? And it turns out it is, but it's kind of hard to do. Okay, and so it takes a little bit of time and thought to do this. Now, what I'm saying right here is it may seem paradoxical here, but the theta coordinate for the main R arm feels any torque or acceleration. Does this thing actually feel any torque or acceleration due to a force in that direction? And you would say, it's not possible to have that happen because this particular force vector goes right through this pivot point here, all right? So it has no lever arm. I'm not going to get anything. It has no moment, okay? And as I say, the line of action hits the theta axis, the axis of the big beam turning. But as this points out why this thing works, is this L-leg pivot is frictionless. It can only transmit a component ml omega squared. That's the centrifugal effect of the force along L. Okay, this is a string. It can't torque this thing, and by you cannot do any torque toward this beam. Well, the beam is kind of being held in constant length, so that wouldn't have any effect at all. But anyway, the idea is that this could certainly put a component of force along L. That's this guy right here. That force is useless, that's useless, but this is useful. This could get to make a connection between this one's velocity and what the beam is doing, okay? So this would cause reverse MRL omega squared on the big arm, just from the geometry that we have here. ML omega squared right here, and then there's an R squared that comes in. Let me see if I got that. Well, it's right here. Okay, so those are the terms that you get, sort of figure out with this. So this would induce that guy. And, well, take that guy over in this side of the equation. That's the total inertia of this system in the configuration it is right now. We've got this term right there. And at the same time, we've got this other guy. Well, we don't. We have, this is a force along L, but we also have a, let's see, we've got here, this is the L squared phi dot. Kind of lost my track. You can see the second guessing is not easy with these Lagrangian problems. In any case, that does check with the Riemann equation. Now, total momentum is present here, and here is something that's going to happen. We've given this thing some angular momentum. The time derivative of that is 0. This thing, the total thing, is 0. And supposedly what's happening is the momentum is coming out of this one and going into that one. So this, and this is thankfully the last slide, I say end of lecture 15. Finally, God damn, this thing is over with. But the basic idea is that you can, with some considerable sweat and effort, write this down for the Chinese, or gravity-free trebuchet. Okay. Now, what we're going to be doing next is, first of all, looking at Hamiltonian mechanics and how good is that at solving this problem algebraically. And the answer is, it's terrible. And it's terrible because of the reasons we already talked about when we did the polar coordinates. And that's because it's more complicated algebra associated with getting the contravariant things. Okay, the Hamiltonian wants to work with that, so Lagrangian wants to work with covariant metric. Okay, it's the contravariant metric that screws the coop here. So I am going to completely change the model. What I want to do, and this will be a problem coming in a weeks, is make a really simple model of just a rotor that's being kept at a constant angular velocity and has a lever attached to that. And see how good that is at throwing something. That can be worked out in UP1 type. Okay? So we're kind of going backwards as we're doing the most advanced stuff and working our way down to the point where we can reduce an idealized trebuchet to UP1. So you, not all the lectures are going to be a mess of algebra like this one was. But I wanted to show you that even that could conceivably yield conceptual results. All right, well, I hope you had a good break and you've got another one coming up. And this problem set is due a week from today. So it's not a hard one. But get started early in case you get tripped by something.